Hello boys and girls, welcome to another episode on our YouTube channel. My name is Craig, I'll be your host in this vlog where I discuss beer and do something with electronics. Today I thought we are going to do something a bit different. Instead of repairing something, I thought let's design and build something. And this came about from an intern at work that asked me a rather stupid question and I wasn't really paying attention. And I said, well, it's easy, just put a regulator in. In case you're wondering, I think he's got a task to build a solar powered cell phone charger, and so of course I said just put a regulator in between your power source and off you go. And he went out and bought the biggest load of rubbish, and then I actually felt quite bad. So I thought, let's design and build our own solar powered cell phone charger, and the goal being, let's do it with components that I have on the desk, on my bench. In other words, not buying anything extra. Today I'm going to be drinking this Dragon Ginger's Double Dragon. I quite like this alcoholic ginger beer. Very refreshing, especially on a hot day like this. So let's get the bench set up and let's have a look and see what we can do. Alright, here we are on the bench. So first, a little bit of theory. So the issue with what I've told my intern, well, it's not completely wrong. Yes, just put a linear regulator in between your power source and your device that you want to charge. It's not the most efficient way of doing things, and we'll get into that now. But for simplicity, what you're going to do, let's say that's our regulator. We'll have an input. We'll have an output, nothing fancy, and so that's an LM7805. The 5 tells us it's 5 volt output regulator. That'll go to ground. The issue with this is, if I want 5 volts here, I need at least 7 volts here. So I'm going to lose 2 volts, and whatever current I'm passing through here, let's say it's 1 amp, times that 2 volts, that gives us 2 watts of power that I'm losing in the regulator. And that's not ideal if we're using a little solar cell like this. The solar cell, I don't know if you can see that, but it can give me 583 milliamp at 6 volts, and that's quite a bit of power to throw away. There has to be a better way of doing this. So if we look at what's inside that little linear regulator, you're going to have something like this, a little transistor. We've dealt with these. So that'll be our input. That'll come out. We'll have a voltage divider of sorts. We're going to come to a new little component here. We'll call that our reference. And this funny little new component down here is called an op-amp. Op-amp is a very simple device. Whatever, it will do its best to drive the output to make the inputs to the same voltage. You have a little plus sign here and a little negative sign here. In other words, these are not actually plus and minus. They call that positive sign the non-inverting input, the negative sign the inverting input. And how this works, our transistor will be off. We have a reference on the non-inverting leg. It's going to drive that output to bring this leg to the same voltage. So it's going to switch that transistor on more, that pass transistor. It will let more voltage through, more current. You'll get a bigger voltage drop here. This voltage will come up, and so eventually we will get to an equilibrium. Like I said, the problem with this is you're going to lose at least 2 volts times whatever current you're passing through there in power. Not the nicest way of doing things. two more things that we've dealt with in a previous episode. We've dealt with a capacitor. We know how a capacitor doesn't like to see a change in voltage. In other words, it is a storage device, an energy storage device, but an electrical energy storage device. The charge builds up on this plate, the negative charges will build up on that plate depending on the polarity, because we have a thing in here called a dielectric. If we take the source out, well, it will do its best to now keep letting that voltage out until it's completely discharged. So that's an electrical storage device. Some very clever guys long ago, Lenz, Faraday, discovered a thing called an inductor. And what they said is, without going into too much detail, if I apply current flow through there, this thing is going to resist the current flow initially and start building up a magnetic field, a magnetic flux around this thing. So the energy will get stored in the magnetic flux. So if you actually looked at the current flow through an inductor, AC current flow, what you would see is the current flow doing this, and this, and this, and this. So we have now a storage device that we can store current in. So we can charge it up, the magnetic field will grow, we take the power away, the magnetic field will collapse and keep pushing the current out in the same direction. Very clever. Around, oh, my memory is fading now. Around the late 70s, early 80s, some very clever people started playing with these storage devices. And I'm just going to swap the page and then I will show you what I... So these clever guys started playing with these energy storage devices, and they started playing with circuits like this. What happens if we could take an inductor, take a capacitor. Notice I'm drawing it polarized just because of the capacitance values that you're going to deal with. I'm going to call that V out. And I'm filming on a high leg tripod, so I'm just moving around it. What happens if I put a switch here? And we put a diode in. Let's call that our positive. What happens if we did something like this? If I could control how long I wanted that switch on. So let's say on this side I'm going to switch the switch on for a little bit, and I switch it off, switch it on for maybe a little bit more. You see where I'm going with this? Well, initially when I switch that switch on, this is going to resist the current flow, but it's going to charge, it's going to get a magnetic flux. When I switch that, it's going to charge that capacitor as well. When I switch the switch off in that period, well, that magnetic field is going to collapse. The capacitor is going to keep my voltage as constant as I can. And if I kept going on like that, well, what do you know? If I had 12 volt here, I could get 6 volt here by regulating that on time. And by regulating this on time, I can make it more efficient. I don't have this huge loss anymore. Quite clever, because of the energy being stored in the magnetic field. So we call this electromagnetic storage, or the voltage or charge being stored in the capacitor and keeping the voltage constant. Well, I'm not having a continuous current flow through these devices, so I need smaller devices, which is always a nice thing, and I have more efficiency because I'm not throwing all this energy away into heat like I was doing with our linear regulator. So what I have in my pot bin is I have a very old MC33063 switching regulator, which has got just that built in. So what I'm going to do is I'm going to get the data sheet here, and we'll go through it, and just some highlights and briefly to the maths. I've already done the maths for you, and then we will move on to the circuit, and then I will build it on a breadboard and we'll check it. So let me get the data sheets out. So here we have a data sheet for MC33063 A. We can see it's a inverting regulator, a buck or boost switching. The circuit we looked at earlier on is a buck. Typically we're going to step the DC voltage down, so we're going to buck the voltage. We could also step it up by boosting it, or we can invert our voltage. So if we had 12 volt, we can get minus 12 volt and fancy things like that. A lot of snot that they mention here, they say designed to be incorporated in step down, step up, and voltage inverting applications with a minimum number of external components. Great. Features operation from 3 to 40 volt, low standby current limiting. Now that's quite interesting, we would like that. Output switch current up to 1.5 amp. It's voltage adjustable on the output voltage. It works on frequency operation up to 100 kilohertz, and it's got a precision 2 volt reference. Then basically they just show you what they have inside the chip, a typical block diagram of it. We have our switch that we're going to use to switch. If you remember the one that we drew. Come on. So that switch there, that's built in. There we have that switch. They talk about their reference. Timing capacitor we will need. Comparator. It will become apparent now why we need this. Supply to the thing, current sense, and the drive to switch it on. Just something of importance, the switch current can handle 1.5 amp using the internal switch. The output switch, in the Darlington connection, we're going to use the Darlington connection. It's got a saturation voltage of 1 volt. Comparator threshold voltage 1.25. It's important, you'll see later on. The timing capacitor, what we expect to see on the timing capacitor. If we come back here, the timing capacitor, it's going to be a little capacitor like this. So what is going to happen, you put voltage in here, the capacitor will charge up, it reach its threshold, and then it will discharge, and so we'll get that waveform. Then they give us typical applications. So there's a step-up converter, step-down converter. That's what we're really interested in, because what I have 2 of these 6 volt solar cells. The problem being is I want a constant 5 volts on the output at half amp. These things can only deliver 583 milliamp at 6 volts. So for today's episode, we're going to do a little buck converter, and we're going to use 12 volts. I've drawn in some stuff here based on the calculations. Don't worry about it, we're going to come back. I've drawn this out properly in a schematic, and I'll go through that with you. My input requirement, I said, well, with HCOM and the state of things that they're in, let's either have our solar cell power supply, so our solar cells in series, our 12 volt solar cells, or a little PP9 volt battery, you're quite familiar with, or a car battery. So we'll have an input range from 7.5 to 14.7 volts. Interestingly, further enough in the data sheet, they give you layouts, and what they do very nicely of them, they give you this bunch of calculations. So if you're doing a step-up converter, you will have different formulas to calculate your different component sizes. step down, same thing, different formulas. All you're trying to do is really basically calculate back based on what they have in this block diagram. So you're trying to calculate here, really, you want a duty cycle, so our output is on, off. For example, what is that time to that time, and based on that you will use certain capacitors, frequencies that you're going to use. How long is it going to be on? Important for your inductor capacitor timer. Your peak current through the switch, the sense resistor for the current, because we want to use current limiting, not particularly in this circuit, but we would like to. And you need these things to calculate your inductor size. So you've got your input voltage minimum, the saturation voltage of the switch, what voltage on the output do we want, and what is the peak, and that will give us the inductor value. Because remember, we said the current flows through the inductor, and the inductance is proportional to the current flow through the inductor. So that's how come we need to calculate inductor size. Then we calculate the output filter capacitor, in other words, how much ripple. So our DC line might look like that, but what is actually happening in there is you've got that happening on it, and how much ripple or noise do we want on it. So I'm going to go, these are not really important, just the inductor that we're going to use, its parameters, and the diode we're going to use. We're going to use a low drop power Schottky. We could use a normal silicon diode, but the voltage drop across it is much higher. It's about 1 volt for 1 amp typically. This has only got 0.45. Remember, the least amount of volt drops we have, or the least sum of volt drops that we have, the better for us. It's less loss in our circuit. So let me get the circuit out, and then we can take it from there. Alright, so here's the basic circuit that I've designed for this. If I was going to build this in reality, what I've said here is we have our 2 solar cells in series giving us our 12 volts. We'll have a blocking diode, I'll explain that now. Or we can have our PP9, again a blocking diode. What that means is this voltage will be able to overcome there, it cannot go back into there, and vice versa. It's just a bit of protection. Here we have our sense resistor. I've made it a 0 ohm resistor, in other words a wire bridge. I'm not interested in limiting the current for this particular circuit. We have our input filter capacitor. We have our timing capacitor. Now these values I've taken from the data sheet, from the formulas that I worked out, so you don't have to. Our voltage comes from the input, it goes through our switch here. Remember our switch collector, our emitter. So we're going to switch that voltage through, depending on what's happening in here with this timing capacitor, and depending what is happening with this little bit of feedback circuit here. So you see I have a voltage divider here, and basically that voltage divider is going to, this should be a 1.2 volt, 1.25 volt, exactly when this voltage is where we want it. So it's going to switch, it's going to charge up our inductor, charge up our capacitor, it's going to switch off, our inductor will release, our capacitor will release, and we will pass out. I've put a little blocking diode here because we don't want whatever coming back from our battery. We've got a little resistor LED just to tell us if the circuit is on. And then what I've got here on the bottom, I just like to make notes when I'm designing a circuit. So I like to mark it here what my desired output, what were my desired parameters and what were my actual calculated parameters. I will make the schematic available. And then what I've done is I've put in 3 circuits, 3 additions to the circuit that we can make it better if we need to. Basically, for the timing capacitor, I've put in a little blocking diode, a little PNP transistor, and there's our timing capacitor. So this will go on leg 3, which will replace that. All it's doing is, if the output is letting us charge the capacitor, we will switch that transistor off. We'll have a volt drop on here. This capacitor will charge up. When that input falls away, that transistor will switch on, because that base leg will be gone. It can't go back through the blocking diode. It will discharge here. In other words, I've created a fixed duration discharge, just to make sure my off time is fixed. I don't think we'll need it unless we reach some very bad instability or whatever. Another circuit that we could put in on the output here, again this is optional, is we could put another inductor capacitor in, and you will see why we might want that. It's just for further filtering, because this output is not going to be that nice. But if it's terrible, we could put in another inductor capacitor. I've just put arbitrary values in just to smooth that output. To go in line with that, I've put in this little circuit. It's a resistor capacitor. This is what is called a snubber. This is actually going to go across your switch like that, any switching device, because what is going to happen, we're going to switch that transistor off in there abruptly. This current has got a discharge, and what it's going to do is the voltage is going to spike here, and that spike, so what you'll see maybe on the oscilloscope is you will see the voltage spike like this, and you'll have this ring. Of course, it will be in the opposite polarity to that, and that's why we have this clamping diode. So in other words, this clamping diode, when that transistor switches off, this diode will pull that line down to ground so that our current can continue to flow back into the ground. Remember, our electricity always wants to go back to the source. So the typical components we're going to use, a few little capacitors, resistors, nothing fancy. What else have we got in here? Well, I'm not going to use this choke, but I'm going to use something similar to that, our inductor, and the brains behind the whole thing. If I just lean up here, to get one would be Sherbet. I'm going blind. There we go. So that, like I say, the brains behind this whole thing is that little IC. So let me build it up on the breadboard, get it back on the bench, and we can show you what we've got, and then we'll take some measurements. Right, here we are, our little breadboard. For those of you not familiar with a breadboard, it's just a nice device that allows us to prototype something very quickly, changing our components by just pushing them in. So you'll see there's a red rail, a blue rail, positive and negative rail, same on that side. Those rails flow north to south, or on the y-axis. These rails here flow on the x-axis. So behind here's a strip on that middle rail that's continuous, then it's obviously broken by that. Here we have our MC33063 our little IC. These two resistors are just our voltage divider over here for our voltage feedback. In there you can see that's our current sensing resistor. It's just a piece of a bridge that goes up. Come on. And that is that resistor up there. And then we have our little LED indication circuit, which is just that. What I'm using is these little Arduino jumper wires just to make bridges to complete the circuits. Up there's our timing capacitors. I've just put two in parallel to give me the 920, so two 460s. There's our switching diode. There's our little inductor. It's a little surface mount inductor that I had, that I just soldered two wires on. Of course, the thing with doing this on a breadboard is you have now created one big aerial. So because we're using frequency, this is very susceptible to noise from other circuits and other things, other devices in the area, cell phones, all sorts of things. We've designed this circuit. I just want to come back here to our calculated. Let's zoom in a little bit. If we go to our calculated values, we've actually designed this circuit to switch on. The minimum frequency we want is 50 kilohertz, so 50,000 times a second. We want a 25 volt millivolt ripple. That's what we require. The other thing is calculated. We are going to get forget the T on, T off. Basically, our frequencies at the inverse of the 50 kilohertz. Reciprocal of that is going to be 20 microseconds, so that's our pulse width. We're saying our T off time is 2.26 microseconds when it's under load. Our T on time will be 17.7. Our timing capacitors, they require. We're not worried about the sensing resistor, we're not going to use that. We're not worried about the inductance because I've put in 100 microhenry that can carry this current. My output capacitor, I said, will be 100 microfarad. My calculated V out will be 6.25, which is fine, minus the blocking diode, the 0.55 of that. So it's still going to be a little bit high, but I'm not worried too much about the circuit because we're not going to plug this into a cell phone. This is not the ultimate circuit that we want. One other little calculation I've put in here is this ERMS. Basically, if you notice our voltage divider, I've got 1K and 4K. If I come back to that ERMS calculation, it means I'm throwing away 1.25 milliamps of current flowing through that. And if you go and do the calculation of power, you'll see it is 7.8 milliwatts of power that I'm throwing away. This ERMS is just basically the Johnson noise or Nyquist noise calculation. All it's saying is temperature has effect on these resistors. As they're sitting there, free electrons will start doing this and create noise in our circuit. That'll be induced into our circuit, but we're saying that the total induced noise from that contribution will only be 2 microvolt, so negligible for us, so that's great. So what I'm going to do, I'm going to hook up my bench power supply to this thing, and we're going to probe it with the oscilloscope and see, do we come close to this even on a breadboard. the points that I'm going to probe, I did not put that diode in because I'm not going to connect it to a cell phone. So basically we ended that point. We've got the LED, so I'm going to probe that point on channel 1. That will be my yellow channel. Channel 2, I'm going to probe that point 2 here by our clamping diode. So basically where the switching is happening, we're going to probe there. We want to see the pulse width and see what ringing we have there. And we're going to probe here by our timing capacitor, because there is some very interesting anomalies in this chip that they don't actually tell us about. And I'm going to show you that by hooking this up to my bench power supply. Like I say, we'll put the yellow probe here, probe channel 1. We will put the blue probe here where our switching is happening, and we will put the magenta or pink probe here by channel 3, which is our timing capacitor. I don't care so much about the voltage supply because I'm driving this with a bench power supply at the moment. So let me get everything hooked up and then we'll come back to it. Alright, here we come to the exciting bit. Let's see what happens inside. As stated earlier on, my channel 1 probe, my yellow probe, is connected to the output of the circuit. So let's just show you. So we're coming here off that LED bridge. My blue probe up here, that one, that is connected to the switching here. My magenta or pink probe, that's connected to my timing capacitors down here. It's over there. And I've put one extra probe up here. That's going to my frequency counter, and that's just connected over that diode. I'm taking it to a frequency counter just to bring it in a little bit more accuracy. So we're happy with everywhere where the probes are placed. Let me extend the tripod and bring this view so you can see what I'm seeing on the scope, and we can take it from there. Right, as you can see, here we have my bench power supply, my frequency counter 0 input, and my scope. Nothing on the scope yet. We'll switch channel 1 on. We can see that there is nothing happening there. So what I'm going to do, just zoom out a bit, I'm going to start switching on our bench power supply and giving it power, and we'll see where this thing turns on. So we're down to 0 volt. We'll switch the channel on and we'll come up 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt. There our frequency counter starts switching on. Only, so yes, 6 volt, 6 volt. On our scope we can see it's risen. It's only 4.42. You can't see it, I've got it. Don't worry, maybe we should rather show you that, and I will count out when I'm switching. So 4.42 at 6 volt, 7 volt. We are now sitting at 5.36, 8 volt, 6.13. What is important to notice, look at that noise. 8 volt, 9 volt, 10 volt, 11 volt, and 12 volt, where we've designed our optimal. We are now sitting at 6.21. RMS voltage down here, 11 volt, 6.18, 6.17 at 10. So it's got quite good regulation. So let's stick with our 12 volts. What I want you to notice on the scope is, look at that. We've got it set to 20 microseconds per division. It's take it out a bit, and oh, look at that ripple. Don't worry too much about that now. Let's switch on our timing circuit. So this is what I wanted you to see. So this is our switch switching on, and this is where our switch switches off over here. Look at that ringing. Oh, look at that ringing. Not too bad. Let's have a look at our timing capacitor. We'll switch channel 2 off, so we can see our capacitor is charging as per the diagram. Now this is all very well and done. We actually have no load on this. The only thing we're driving is the LED, and if we did a let's do a quick calculation, power wise, efficiency. What is the circuit doing? We've got a 180 ohm resistor, so we're going to say what is it, 6.15 divided by 180, give me our current squared times 180. So we're pulling 210 milliwatts divided by the 216 that we're putting in. So we're pulling 210 milliwatts divided by the 216 milliwatts that we're putting in. So our circuit is running at 97% efficiency with minimal load. So you can already see that this is a much more efficient way of doing it. So what I'm going to do, let's just switch these channels off. I'm going to put this resistor into the circuit. It's a 10 ohm 10 watt resistor. So basically what I've said is, if we put this in, it should load it and it should pull roughly about half an amp. So I'm just going to put that across the output, and we will see what we get then. Right. Oh, interesting. So we've put our 10 watt resistor in. Look at that. Look at that ringing. You just bring out the time a little bit, and then you can see, oh, look at that ringing. This is the drawback to switch mode. I'm going to switch on our switching. What we can see is our pulse width. If I drop the voltage, you see the pulse becomes wider. As our voltage gets into where we want, it becomes, the pulse width becomes less. Let's come back to our 12 volts. Yo. Let's have a look at our switching capacitor. Interesting. Can you see the knee in the switching capacitor? We'll switch off channel 1. Switch off channel 2. Let's bring it down. Can you see what is happening? Let's get a decent pointer. Look at the profile. It's accelerated over there. That is the chip doing that to compensate. So the chip is now accelerating the time on requirement because it feels it doesn't have enough. Remember this circuit we talked about up here? Well, that might be able to help us with that. I'm going to switch off the timing capacitor because we don't really care about it. We'll go back to this. Let's zoom out. Let's look at that ringing. Notice that that ringing is out of phase, or the inverse to our output. Remember I said the inductor resists the flow of changing current, but it does so also by reversing its polarity. There we can see that the polarity is reversed. We could of course look at the value from that peak to that trough, or that peak to that peak. We can get the frequency, and we could devise a snubber circuit, which we talked about over here, our snubber circuit, to get rid of that ringing. So, but all in all, if I go back to my 20 microseconds, even with those peaks, I'm still, I don't know if you can see it down there, I'm still getting 5.9 volts RMS out. I could go to filter that horrible peak and trough out. We could go with this circuit over here. So all in all, it's not a bad circuit. How efficient is this circuit? Well, we've got 5.9 volts on the output. Our load currently is the series, well, the resistor for the LED, so it's 1 divided by 180 for the LED, plus 1 divided by 10 for our load resistor. The reciprocal of that, 9.474. We've got 5.9 volts, 5.9 divided by 9.474 will give us our current. Square of the current times the 9.474 will give me 3.67 watts. What you can see is we're pulling 4.667 watts, so we divide it by 4.667 times 100, and our efficiency 78%. So even with a heavy load, we are beating our linear regulator hands down. So 78% efficiency on a breadboard without any mitigating circuits. I'm very, very impressed. Of course, this is not the ideal circuit to build. We don't really want to put our two solar cells in parallel. What we'd rather do, in series, what we'd rather do is put them in parallel, because we can give you more power, or better use the power. Oh, look at that ringing. So I'm going to call this part 1, and what we'll do is come back and design something in part 2. Just as a matter of fact, there's interest. Look at that, spot on. 49.8532 kilohertz. Really, I think, let's see, 49.87 0.897 divided by 50. Really, we are, so the deviation out maybe 0.01% on our calculated frequency. So even that is not bad for a breadboard. So we've got a 78% efficiency on our switch mode power supply. Sure, we've got a bit of ringing. Just one thing to say about this ringing. These peaks are very important, because why we might need to put a snubber in is we might destroy that switch in there. Luckily for us, we're sitting at 2 volts per division, so it's what, so it's 3 on our switch side. It's 5 volts, 5, 10, 15 volt, so that's not a problem because our switch can handle 40 volts before it breaks down. So we'll set it up for the last shot, but thank you. I'm quite impressed with this MC33063 IC. Very efficient. I know guys have had problems with it. We've done it on a breadboard and we didn't seem to have too many problems, and we haven't had to put too many mitigating circuits in to kill it. So let's set up for the last shot and we'll see you there. So boys and girls, we come to the end of another episode. I hope you found that interesting. I hope you learned something. Yes, we only looked at the buck stage of this. The circuit is able to do a boost, and I think for part 2 I'm going to see if we can design a buck boost. In other words, we can put in a low voltage, and what we really require, the chip will step up the output voltage but keep the current, and if we put in a higher voltage, it will do the step down and again keep the current. This time though, we will limit the current, because we're going to say we only want to give the cell phone half an amp, because if you dig into the USB specifications for this, it comes in increments of 0.25, 0.51, 1.52, and so it goes on. So we will limit it to half an amp, and we will want to design our circuit to either take our 2 solar cells in parallel, so the voltage may be lower, the sun efficiency or irradiance is bad, it will step the voltage up, or we'll use a PP9, or we can use a car battery. Obviously with our power provider in South Africa, this might be actually a viable thing. So we'll save that for part 2. I will design the circuit, and we will see if this chip again can deliver what we want. Like I said, I hope you found that interesting. I hope it was as much fun for you as it was for me. Until next time, take care. Cheers.